So normally when we are making a linear model, we have 2 points of data that we know, and they're in a straight line, and they connect perfectly, and we can easily create an equation that fits both of those. But what if the numbers that you have aren't exactly perfect? Like they're not perfectly in a straight line. They're they're a little all over the place. What we need to do with that then is we need to create what is called a line of best fit, where I might have a series of lines that are going, they might be going around, up and down, etc. In approximately the same place. So if I, for example, I might have an axis here. Well, I think we'll do a better one than that. So have an axis here. And I'm going to put some random dots on my page. But what you'll notice is that these dots are, they're all right. They're a little all over the place. But I think, remembering back to Unit 1, when we're talking about statistics, that we could describe this as a positive linear relationship. Does anyone disagree with me on that? All right. So these dots are following in a relatively linear and positive fashion. What we can do is we can create a line of best fit that approximates the values of the equations that we've got going on here. And generally the way we do it is we look for, this is where I'm going to need my ruler again. And what I'm going to do is I'm going to try and line up the left dot with the right dot. So the leftmost dot with the rightmost dot. And from there, I'm going to draw a line that passes through those 2 points. All right. And looking at the line that I've made, what do you notice about the rough distance of these points from the line and these points from the line? What do you notice about them in terms of how far away they are? All right, because if you look, if I were to take the average distance, so if I were to look at this distance here, this distance here, this distance here, this distance here, and I were to compare them with the distances from here, 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 and here, they would even out. Approximately, it would even out. All right, so this isn't a perfect fit, but this is the line of best fit. So what I could then do is, if I know this coordinate here, so if I know this is, this could be 1, 5, and this one over here is, I don't know, 20, 25. I could make an equation that approximates the line of best fit, and then I can make predictions regarding where everything should be. All right. So what this looks like in practice is when we are dealing with things that are relatively close together in terms of their grouping, but they're not a perfectly straight line. So for that, we're going to use an example of a distance versus time chart. All right, and that looks something like this. All right. So what you'll notice here is that, again, the leftmost dot and the rightmost dot have been connected with a line, and it has been extended to here. And you'll notice that that overall the dots are pretty evenly far apart or distantly from where the line is. I say approximately. It's not perfect. I mean, this line here, but it's still what you would describe as a positive linear relationship. All right. So from here, the question I'm going to ask is, what is the line or the equation for the line of best fit? All right. But what is the equation for the line of best fit? So where would you say approximately that coordinate is? Where would you say it approximately is? And then also, where would you say that point is? All right, the one on the right is much easier because it is 3,500, comma, and then it is on the blue line halfway between 300 and 350. So that makes it nice and easy. That's 325. The other one is a little bit more flexible. All right. People are going to disagree, but as long as you're within, a reasonable margin of error, you can work with that. So looking at my chart here, so I've got an opening bid of 300,70. Anyone here want to have a swing at that one? Because I reckon that's a pretty good guess, because 75 is here, 250 is here, so it's a little under 75 and a little higher than 250. So 370, I think, is a perfect place to start. So 300,70, good place to start. From there, what we need to do is we need to actually make our equation. So determine the equation in terms of T and D. So remember, we have to use T, we have to use D. And so our equation is going to be T equals A plus BD. And from that, we'll need to use our CAS. So let's pull up our CAS. Go to spreadsheet, or not spreadsheet, go to statistics. We'll get rid of this data here. And we will put in 370, and then the other one, which was 3,500 and 325. Calc regression, linear regression. We're going to copy the formula because we might need it to do some other stuff later. Hit OK, and there is our there is our equation. All right. So the time it will take will follow what it says on our CAS, the formula. So our A value is going to be 46.09375. So that's, hang on, I don't want that one, I want the nice thin one. So T is going to be equal to 46.09375 plus 0.796875 D. All right. So we have that now. Use the line to predict the traveling times between two cities that are 2,500 kilometers apart and 4,500 kilometers apart. So again, we can go back to our CAS for this. Makes our lives much easier because we copied it into our Y1. Calc, analysis, and from here we can go along and we can find 2,500. Hit OK. And there's our point there, 2,500, 245.3125. So according to our line, 2,500 should be about 245, which makes sense. That's what it looks like on our graph here. So that's 2,500, 245.3125. Close bracket. All right, and then the next question is, what if we extend this graph further and we go to 4,500? So it's going to end up up here somewhere. So what about 4,500? What's that one going to be? Going back to our CAS. We're going to move along, and we're going to go to 4,500. We're going to say it's going to be a domain error, so we're going to zoom out a little bit. And then analysis, trace, 4,500. And it's going to come along as 404.6875. All right. $404.6875. And then we can go back to the question. And it says, when making the predictions in B, so when we are using our line of best fit to make predictions, are we interpolating or extrapolating? So these are two words that come from bivariate data when we're making predictions using straight lines. So, are we making interpolations or extrapolations using our equation? All right. All right, so for 2,500 kilometers, when we were working out that using our line, was that an interpolation or an extrapolation? All right. So think about the numbers that we had to work with on our data. We joined up a point at 300 and a point at 3,500. 2,500 fits between those 2 points and therefore is inside the range of our source data, which means it's an interpolation, which means that we can reasonably trust it. it's reasonably reliable. However, 4,500 is outside the range of data, which means we can trust it less. Now, it is a linear model still. So the predictions are generally pretty good. However, because it is an extrapolation, we are extending the graph beyond the source data that we have. It is not as trustworthy. So on our graph, in big red letters, we can write this is interpolation. And this here is all right, because it's all about where we got our equation from. We got our equation from 0 to 3,500. 2,500 fits nice in between, whereas 4,500 is outside that. Therefore, it's not as reliable. Complete the following sentence by filling in the box. When the distance traveled is increased by 100 kilometers, the traveling time increases by blank minutes. All right, so this is where we need to go back to our original equation that we created using the line of best fit, which is this one down the bottom here. This is for every 1 kilometer, it increases by 0.7968 minutes. Well, I'm going to take that, multiply that by 100, and that means for every 100 kilometers, 100 kilometers equals 79.68 minutes. About 80 minutes. All right, so 6G part 2 and part 3, please. And